Hello everyone and welcome back to our finite automata series of the um, automata and formal languages class. If you have been following the last few classes, basically what we have started working in terms of formalizing computation has been the idea of studying a mathematical formulation of what computation means in terms of determining whether a sequence of input symbols are accepted by a machine. And we showed that there are certain kinds of strings made of symbols, and these symbols could be anything. It could be binary numbers, it could be letters, it could be any form of ideology or idea that you have that you can formulate, and then you can utilize that into a set, and then you can create a finite machine, a finite state machine, which we call the finite automata, or a deterministic finite automaton rather. And we showed that if we can find a deterministic finite automaton for a particular set of strings, and if we group this set of strings together, we can call these strings regular languages. Or rather strings belonging to a regular language. And we define a regular language being a language or set of strings that are accepted by some finite automaton. Then we looked at a mechanism to combine regular languages to come up with other regular languages off of some already known regular languages by creating unions or intersections of languages. And we showed that those languages will be regular. Or in other words, we showed that, yes, the union or intersection of regular languages are themselves regular, in that we can find an automaton, and we proved this by construction, that could recognize the union or intersection of two languages. However, when we attempted to prove and to show that the concatenation of two regular languages is regular, we found that there is a problem that we could not solve by our already created toolbox and that we have. In other words, we cannot use deterministic finite automata to show and to construct a finite automata that recognizes the intersection, or rather the concatenation of two regular languages. That was the problem, and I promised that we will build a toolbox that could help with proving this theorem. And the idea that we will be discovering today in this unit is going to be non-determinism. We'll see what non-determinism effectively is, what kind of toolbox it gives us, and how it would be useful in showing and proving the closure properties of regular operations and regular languages. Non-determinism is a very useful concept that it has had a very important impact, a great impact on the theory of computation. Whatever we have worked so far with the finite automaton and creating our finite state machines was that at every step of the computation, the result of the next step was completely deterministic. We knew that if we are in such and such step in our computation and we see such and such symbol, where exactly should we go and how exactly should our machine proceed computing. So when the machine is in a given state and it reads a given input symbol, it exactly knows what state it should go to. It is fully determined. In other words, this machine uses a deterministic computation. In non-deterministic machines, however, at any given state, the machine may have several choices. There may be several choices that exist for the next possible state to go to at that point. If you think of non-deterministic finite automata, or rather non-determinism, it's basically a generalization of your computation, or a generalization of the computation of the state machine or the automaton that you have. As a result of this, any deterministic finite automata will be effectively a a non-deterministic one, because if in our definition, in our formulation, deterministic finite automaton are rather constrained or a specialized case of non-deterministic finite automata. So non-determinism is basically a generalization of the deterministic finite automata we have, and as a result of that, any deterministic finite automaton will be a non-deterministic one by nature of the generalizations, because any special case of something general, would be, by virtue of it being specialized, will be a form of its generalization. So non-deterministic finite automata effectively enjoy from some additional features that deterministic ones don't have. And I'll go over this for you so you'll see what's going to happen. Now, if I show you the picture, like the state machine that you see at the bottom here, and if I tell you what kind of state machine it is, obviously you would say it's a determinist, it's a finite automaton. It's a finite state machine. It has a set of states, finite set of states, and it has a finite set of transitions that go from any state to another state. However, and also it has a start state and it has a set of accept states. In particular, one member of the states, set of states, Q sub 4, Q4 is the accept state. However, in a more, I would say, close inspection of this machine, you would notice that this machine is a little bit different than the ones that we have taught so far. Specifically, if you look at this machine, state Q1, of course it has a transition for symbol 0, but for symbol 1 it has two transitions. It can either go to Q sub 2 or it can go back to Q sub 1. Same with state Q sub 4. Actually, the Q sub 3, however, is a state in which there is no outgoing transition for symbol 0. When you're in state sub 3, Q sub 3, and you see 0, your machine will have no state to proceed to. Also, one of these transitions, in fact, transition from Q sub 2 to Q sub 3, has a label that we haven't seen so far. In our finite automaton, for every state, we had a set of outgoing transitions for every single symbol we encounter. With Q sub 2, we don't have an outgoing transition for symbol 1, but what we do have is an outgoing transition for symbol epsilon. And if you remember, symbol epsilon is an empty string. So what is going to happen? What are the differences between a finite automaton that is deterministic or one that is not deterministic? Let's first set some language straight. Both deterministic and non-deterministic finite automata are finite automata. The deterministic ones, from this point on, we call them DFAs, basically abbreviated deterministic finite automaton. And the non-deterministic ones, we call them NFAs, non-deterministic finite automaton. So the difference between a DFA and an NFA, from the inspection that we have earlier, will become clear, and we formalize this later on in our formal definition. Every state in a DFA has always exactly one outgoing transition for every symbol in the alphabet. So if you're in state sub Q sub 1 and your alphabet is 0, 1, 2, and 3, then you would have a transition for 0, a transition for 1, a transition for 2, and a transition for 3. And every state in your DFA must have one and only one outgoing transition for every input alphabet symbol. However, in NFAs, there are two. This requirement is relaxed, so to speak. There may be more than one outgoing transition per symbol. You may have more than one outgoing transitions for any symbol. That includes a finite number of outgoing transitions. In fact, you could have outgoing transitions to every state in your state machine for a given symbol. Also, there may be no outgoing transitions for a given symbol. For example, in the finite automaton up here, for symbol 1 from state Q1, there was two outgoing transitions out of Q sub 1, but Q sub 2 doesn't have any outgoing transitions for symbol 1. So these the requirements that a DFA had, that every input symbol must have an outgoing transitions for every single state, that is not the case in NFAs. Also, in DFAs, the labels for transitions are from your alphabet. But in NFAs, the labels are from alphabet union with the empty string, meaning that the empty string could be a label for your outgoing transitions. What this means is that when you're in a state that has an outgoing transition labeled epsilon, that means that from that state, your machine could transition to the destination of that transition arrow without reading any symbols. So basically, your state could be in the same state that it is, or it could also go to a new state where the label epsilon, or rather the transition with label epsilon, points to. And we'll talk about this in more detail. So how does a finite automaton that is non-deterministic, or in other words, how does an NFA compute? We formalized the computation of a DFA, and we said that when a string comes in, your DFA starts in the start state, reads the first symbol, looks at the transition, and then processes, goes to the next state, then reads the next symbol, and then for that state, it sees which arrow has the label of that symbol. It moves through the destination, and it keeps going through all the states by reading each symbol and taking its appropriate transition and going out. However, we know that the NFAs could have no transition going out of a state for a symbol, could have multiple transitions going out of a state for a symbol, or could have transitions with epsilon. So how do they actually compute? It's actually fairly straightforward and easy. When your machine is in some state and sees more than one outgoing transition for a symbol, it basically splits its operations into multiple operations. Effectively, if you want to think about it, your machine at that state is going to branch out. So if you're in a state that has 3 outgoing transitions labeled with the same symbol, your computation is going to branch into 3 copies of computation, 1 for each of the outgoing transitions. Remember, with the DFAs, you had only 1 outgoing transition, so you exactly knew from state X with this label symbol, you go to state Y. Now, so that's just 1 branch of computation. In NFAs, though, because you may have multiple outgoing transitions, then if you're in state X, and let's say that there are 3 outgoing transitions to states U, V, and W, then if your machine reads the symbol, then from state X, it creates 3 copies of it, 1 for state U, 1 for state V, and 1 for state W. I'll show you in a little bit, and so don't worry about this at this point, just kind of I'm explaining what's going to happen. It's basically, if you want to think about it, it's like forking in a parallel processing situation. For example, in a parallel processing situation is when you're sending out a kernel and you're creating 3 computational units off of it, and you're branching it 3 times, or rather creating a fork with 3 operations, then it's going to create 3 threads of operations simultaneously in parallel, 1 for each of the computational threads that you have. What happens when you see a transition labeled with epsilon? Well, this is also easy to see how it works. When you're in a state that has a transition outgoing labeled epsilon, then your machine will basically take the transition before reading anything, because epsilon is an empty string. So when you're in a state with an outgoing epsilon transition, your machine could be in that state, or it could go to the destination of the epsilon transition without reading any symbols. So that gives your machine to be able to process without reading anything from the input string. So that gives you a little bit more flexibility in that sense as well. And what happens when you are in a state that has no outgoing transition for a symbol, and your alphabet and your string has a symbol? So if such a situation occurred, if you are effectively reading from the string a symbol, and then you're in a state that doesn't have an outgoing transition for that symbol that you read, that branch of computation of your NFA will die at that point. And it also, so that thread dies, that copy of the machine dies, and all the computation with it dies as well. So by basically combining these three flexibilities, having multiple transitions, your machine can branch out. Effectively, when we see this a little bit later, it's like guessing. Then having an epsilon transition also as a means or a mechanism of proceeding through your computation before reading, without reading anything, and the seeing no transition out of a state for a symbol, that means that the guess that your machine has made was wrong, so it's rejected, so that kills that process of that branch of the guess. And so so these three concepts together would effectively allow your NFA to compute much like the DFA, and once your string is completed, then your NFA looks at the states it is in, and if any one of those states in any of the branches of computation is one of the accept states, then your machine accepts that string. If none of the states in all of the branches of your computation are not, any of them are not accept states, then your machine will reject that string. So let's take a look at an example and see how this this NFA works. This is the same NFA that we talked about earlier a couple of slides ago, and I'm going to show you a few of or rather a couple of examples of how it processes, and then you'll see how it works, and then we can take a look and see what are the means of its computation, and what kind of strings does it accept, and so on. And then we'll basically see a couple more NFAs before we get to formally defining NFAs and proving that NFAs and DFAs indeed are capable of understanding and recognizing the same languages. DFAs and NFAs effectively are the same creature. Okay, so before I actually go ahead and start working and showing you the computation of this NFA n sub 1, let me just draw a simple picture about how finite automaton, DFA, deterministic and non-deterministic finite automaton actually compute. If you think about your automata in terms of a deterministic one, you start from a start state, and then for every symbol you read, and then you proceed, and then you keep going, and then you keep going, and then at the end of the string, and so if these are your symbols in the string, if these are symbols in your string, then you basically look at this last one, and then you see, is it a accept state or not? If it was, then you accept. If it wasn't, then you reject that string. In non-deterministic finite automaton, you start from a single start state, and then for each input alphabet, you look at the transitions that are outgoing, and then you go to the next state. Now, if you have multiple outgoing transitions, you might actually branch this into, say, if you had two outgoing transitions for the second symbol, for example, here, then you branch out into two, and then for the next one, let's say that you may have had 3 outgoing transitions there. For this one, you may have had just 1 outgoing transition. So you keep going, and then if any of these don't have any outgoing transitions, then they will effectively die out. And so you're basically, your automaton keeps track of a trees, or rather a tree of possibilities. So, and I butchered the word possibilities in terms of its spelling, but it doesn't matter. And so if any of the last states, if any of these if any of these, after you completed the string, if any of those states were an accept state, then you accept. Otherwise, you reject. So you see, in the DFA, for every state you have one possible transition, and then you keep going through them, and then you look at the last step. If that wasn't one of the accept states, you accept. Otherwise, you reject. In an NF, so this is a DFA computation. In an NFA computation, At any step, you may have multiple choices. You may have no choices. If you don't have any choices, then that branch dies. So, for example, this branch didn't have any choices. Then it would die. Otherwise, you basically keep processing, and then when you're done with your string, you would end up with a bunch of states, of possible states, end states, and if any of those were an accept state, you accept. Otherwise, your machine would reject that branch, that string. So that's how these machines work. So the example that we have here, an FAN sub 1, starts from Q sub 0, and then on symbol 0, it stays in Q sub 0. Then on symbol 1, if it sees symbol 1, from Q sorry, you start from Q sub 1, and on symbol 0, you stay in Q sub 0. You stayed in Q sub 1, and then on symbol 1, I should have called these, or rather your book should have called this A and B. And so on symbol 1, you have two options. You could stay in Q sub 1, or you could go to Q sub 2. And so you can see that in state Q sub 1, symbol 1 would be a guessing symbol. If your computation is in Q sub 1 and it sees 1, it guesses to stay in Q sub 1. That would start a branch of computation, or it guesses to go to Q sub 2, and it starts out another branch of computation. Now, in Q sub 2, you have an epsilon state, which means that if you are in a branch of computation that ends up in Q sub 2, it could also immediately go to Q sub 3, because in Q sub 2, your machine proceeds to the next step without reading any symbols. So effectively, one way of looking at this computation is that you may stay in Q sub 2, or you may proceed to go to Q sub 3 as a result of or without reading any input symbols. And finally, when you're in Q sub 2, if you read a symbol 1, then you just have no outgoing transition, so that ends that branch of computation there. Similar with Q sub 3 and symbol 0. So if you are in Q sub 3 and your next symbol is 0, then that branch of computation stops because there is no outgoing transition for Q sub 3. So let's see what is the result of the computation of this machine over string 0, 1, 0, 1, 1, and 0. So we want to see whether this machine accepts the string 0, 1, 0, 1, 1, 0, or rejects it. So the way that my computation works, I'm going to do this horizontally and vertically for you just to see how to write this down. It doesn't matter the way that you represent this computation. The idea effectively is that you start from the start state, you read a symbol, and then you take the transitions, outgoing transitions for that symbol. If you have multiple choices, then you branch out from that point on. So for this case, we start from Q sub 1, and then we see symbol 0. And so what are we going to do with symbol 0? We see that Q sub 1 with symbol 0 has only one transition, which goes back to Q sub 1. So we're going to stay in Q sub 1. Then we will read symbol 1. Now, over reading symbol 1, our machine has two choices: stay in Q sub 1 or go to Q sub 2. So my machine at this point will effectively branch out to two copies of itself. One will stay in Q sub 1, and one will go to Q sub 2 for symbol 1. However, notice that once you are in Q sub 2, and we're still processing the state Q sub 1. Once we are in Q sub 2, effectively we have an outgoing transition from there with epsilon. That means that once my machine read symbol 1 ended up in Q sub 2, it also has another choice. Keep going. So it's going to go to Q sub 3 as well. So upon reading symbol 1, my machine could actually go to Q sub 2, skip it, and go to Q sub 3. Because remember, my machine will have when it's in Q sub 2, it has an outgoing, a possible transition without reading any further symbols, right? So if you want to think about this part of my computation, effectively, when I'm in Q sub 1 and I read a 1, you can kind of sort of think about this as having actually two transitions for a 1, or basically a 1 and an epsilon, because you could go into Q sub 2, or you could go into Q sub 2 and still keep going because of this epsilon here, right? So with the reading of symbol 1, if you are in Q sub 1, you have three options. You can stay in Q sub 1, you can go to Q sub 2, or you can go straight to Q sub 3, skipping Q sub 2. So that's your three choices that you have there. Okay. Next, we want to see what's going to happen when we read symbol 0. However, when we read symbol 0, we have to process 3 states. So we could effectively keep our fingers on 2 of the states and then process the ones that's left. And then when we process that state with symbol 0, then we keep going to the other symbol and the other symbol. So effectively, now we have 3 copies of machine, that for each of those copies of the machine, just like a deterministic finite automaton, we have to process it. So what's going to happen if we are in Q sub 3 and we read symbol 0? Nothing's going to happen because we don't have any outgoing transition out of Q sub 3 with symbol 0. So this process is going to die from this point. There's no transition out. In Q sub 2, when we see a 0, then we proceed to go to Q sub 3. And then in Q sub 1 with symbol 0, we proceed to Q sub 1. Okay. Now let's take a look at the next symbol, this one over here. Let me just clean up this right up here, and we'll get a better. So this is for 0, and then let me do this one here, and I'm going to see now what's going to happen when the next symbol is 1. So the first branch of Q sub 3 died, so that's no problem. The next branch of Q sub 3 here, over a 1, it's going to go to Q sub 4. So this is going to go to Q sub 4. And then Q sub 1 with a reading a 1. Remember, we had 3 choices. Stay in Q sub 1, go to Q sub 2, or go to Q sub 2, and then since there is an epsilon transition, keep going to Q sub 3. So we still have 3 choices here, just like we had earlier. And these 3 choices are going to be Q sub 3, Q sub 2, and Q sub 1. Just like we had earlier for a 1 here, we're going to have another set here. Now we have 4 states to process. So for the next symbol, which is a 1, that we are going to process, we basically end up with 4 states. So let's see how that will do for the next one. Q sub 4, when it reads a 1, it stays in Q sub 4, so that's easy. Then Q sub 3, when it reads a 1, it goes to Q sub 4. Q sub 2 on a 1 dies because with a 1 there is no outgoing transition for it. And then Q sub 1 with a 1 splits into 3 branches. Remember, we did that earlier. So with a 1, if you're in Q sub 1, if you see a 1, you may stay in Q sub 1, or go to Q sub 2, or go to Q sub 2, and then through Q sub 2 proceed to Q sub 3 over this epsilon transition. So we're going to have, again, 3 copies Q sub 3, Q sub 2, and Q sub 1. Okay, and finally we'll have the symbol 0. And what's going to happen when we read symbol 0? Q sub 4 is going to stay in Q sub 4. Q sub 3's this Q sub 4 over symbol 0 is going to also go to Q sub 4. Q sub 3 over symbol 0, it doesn't have any outgoing transition, so that process is going to die. Q sub 2 for a symbol 0 could go to Q sub 3. And then Q sub 1 for symbol 0 will stay in Q sub 1. So now, after I process my my string, I end up with 4 states that my machine is in, and 2 of these 4 states are actually accept states. These are not accept states. So now my machine looks at seeing if any of these states that I ended up at, if any of them is among the accept states. If there is one accept states at least, then my machine accepts. So by result, because both of these are accept states, then the NFA n sub 1 accepts. Let's call this W. It accepts W. Okay. So then again, the way that your machine processes is that it's going to go, it's going to start with the start state, reads the first symbol, and then transitions, takes all of the outgoing transitions that is coming out of the start state with the first symbol. Then it's going to go to all of the states that it ended up. For the next symbol, it's going to see and follow all of their transitions, and then keeps processing in that sense. Anytime you have a choice, you branch out, and then when you're done with your string, if any of the states that you have at your hand is a accept state, then you are then your machine accepts that string. I'm going to do another one with this with the symbol. Let's call it W sub 2. Call this W sub 1. W sub 1, and let's see if this machine accepts this symbol 0 1 1 1 0. Okay, so let's see what's going to happen. So we start with Q sub 1. I'm going to do this now vertically. You'll see effectively how this works vertically. So the first symbol is symbol 0, and we'll see what's going to happen when we read symbol 0. So Q sub 1 over symbol 0, it has only one transition that it can take, and that is to stay in Q sub 1. So if you read symbol 0, you stay in Q sub 1, no problem. Then the next symbol is a 1. So on a 1, your Q sub 1 has 3 choices. Branch out, stay in Q sub 1, go to Q sub 2, or go to Q sub 2 and then proceed to Q sub 3 because there's an epsilon transition. So then again, here we have actually 3 transitions that come out. For 1, we could stay in Q sub 1, go to Q sub 2, or go to Q sub 3. The next symbol is another 1. Now, Q sub 2 doesn't have any outgoing transitions for 1, so that branch dies there. Q sub 3, there's a 1 transition labeled 1, so that's going to go to Q sub 4. And then, just like the previous case, Q sub 1 has 3 outgoing branches that could take, stay in Q sub 1, go to Q sub 2, or go to Q sub 2, and then over the epsilon transition, go to Q sub 3. So you're going to end up with 3 transitions out there. So that's the second one. So then the next one, you've got another symbol 1 that you're reading there. So Q sub 4, it's going to stay in Q sub 4. Q sub 3 is going to go to Q sub 4. Q sub 2 is going to die, and then Q sub 1 is going to branch out into 3 states. Stay in Q1, go to Q2, or go to Q3. And finally, we have a 0 symbol. So Q sub 4 here and here, they are going to stay in Q sub 4 because we have a transition going back to Q sub 4 over 0. Same here. Q sub 3 with a 0 has no transition, so that branch is going to die there. Q sub 2 with a 0 has a transition to Q sub 3, so this guy is going to go to Q sub 3. And Q sub 1 has a transition back to itself over 0, so it's going to stay in Q sub 1. And so these two states are, now that I'm done with my string, these two states are accept states. So my machine in sub 1 also accepts W sub 2. Alright, so let's try a couple of examples of strings that this machine does not recognize. Let's talk about string W sub 3 to be the string 1 or rather 1 0 0 0 and 1. Let's see what happens with this string. So we start with Q sub 1. So we start at Q sub 1, which is our start state. What's going to happen, as you have here with the machine with symbol 1, Q sub 1 is going to branch into 3 states: Q sub 1, Q sub 2, and then Q sub 3. So we are going to branch out, reading symbol 1 into 3 states: Q sub 3, Q sub 2, and Q sub 1. Okay. Then Q sub 3 doesn't have an outgoing for 0, so it breaks there. Q sub 2 with a 0, it's going to go to Q sub 2. It's going to go to Q sub 3 over a 0. Go to Q sub 3. And then Q sub 1 with a 0 transition, it is going to stay in Q sub 1. Q sub 3 for the next 0, so we processed this first 0, we processed the next 0, now we're going to process this 0. We're not going to have any outgoing transition for Q sub 3, so that's going to die. And then Q sub 1 with the 0 is going to transition back into itself, so that's going to stay in Q sub 0. Now for this third 0 here, Q sub 1 has only one transition, so it's going to stay in Q sub 1. And finally, for the last symbol, which is a 1, we are going to have 3 outgoing transitions. Go to Q sub 3, go to Q sub 2, or stay in Q sub 1. Now we're done with our symbols, but none of these states is an accept state. So none of these is an accept state. So NFA n sub 2 therefore rejects W sub 3 here. NFA n sub 1. And so if you take a close look at what's going to happen in this NFA, actually, you will see that this NFA is going to stay in Q sub 1 regardless of whatever it's reading, as long as it's 0. However, when it sees a 1, it's going to take a guess. So it's going to branch out into Q sub 2 and Q sub 3, and also it's going to stay in Q sub 1 as well. Now, when it is in Q sub 3, if it sees a 1, it ends up in an accept state and it's going to stay in the accept state. So effectively, one of the kinds of strings that this NFA recognizes is if the string contains two ones, two consecutive ones. So if you see the first one, you're going to branch into Q sub 3, and for the next one, you're going to branch into Q sub, or you're going to proceed to Q sub 4, and that is your accept state. And then from that point on, you're going to stay there for either 0 or 1. So if your string has two ones, you're going to accept it. Also, when you're in Q sub 2, you are going to go over a 0 to Q sub 3, which then over a 1 takes you in Q sub 4, which is an accept state. So when your machine sees the first one, then it's going to take a guess. Do I have two ones or do I have a 1, 0, 1? And if any of these two is true, then you're going to end up in an accept state. Otherwise, the computation branch for that guess is going to die. So see again, when you see the first one, you're going to go into either Q sub 2 or Q sub 3. Right? Now Q sub 3 takes you with a 1 into Q sub 4, which is an accept state, and Q sub 2 will wait for a 0 and then a 1, and then it takes you to a Q sub 3. And these guesses were both done over reading a 1. So your machine basically, as it reads the string, it basically looks for two consecutive ones or two ones split by one single 0 between them. And it basically looks for these two substrings. If your string has either one of these two substrings, then it's going to be accepted by your machine. If it doesn't, it's going to be rejected. And as we saw here with this processing, when my machine saw the first one, it basically guessed, am I going to have two ones or am I going to have a 1, 0, 1? And when it didn't have a two ones or a 1, 0, 1, which is the case here, these two branches of operation, these two branches of the guesses died. And then my machine stayed in its waiting for the next one to start its own two guesses. Am I going to have two ones or am I going to have a 1, 0, 1? And then when that guess happened here, since there was no more symbols after that, then these branches of computations died as well, which means that my machine did not end up in an accept state, so it rejected that string. So then again, I'm going to go over this one more time to kind of let you see what happened. Basically, having multiple choices, multiple outgoing transitions for a state gave my machine a means of performing a guess and then testing that guess over the next sequences of symbols to see and test them to see if they end up in an accept state or not. And then when there was no outgoing transition for my guess out of a future state, then that computation guess died, which is the case down here, down here, down here, and also it was the case up here, and here, and it was also the case in these two cases up here, that my machine took a guess that this one is either the beginning of a 1, 1 or the beginning of a 1, 0, 1. If it wasn't, those guesses will die. So, so as you see, non-deterministic finite automaton are very useful in several respects. And later on we will show that any NFA can be converted into an equivalent DFA. And so as a result of NFAs being generalizations and allowing us building a machine that could basically guess and then prove its guesses, building NFAs are much easier and much more direct than constructing DFAs directly. In fact, many NFAs that recognize the same language as some DFA will do will have far fewer states than their DFA counterparts. And so so this is really a very good toolbox for us to be able to work from this point on. And later on we see that the proving of our closure properties with NFAs are actually much easier. compared to what we did with the DFA for the union and the intersection closures, as well as the negation closures. Also, NFAs are really important in that they are when we go into more powerful computational models such as push-down automata and even Turing machine, non-determinism would be a powerful concept there. However, non-determinism in more complex automata, they will have much power than their deterministic counterparts, and in most cases, working with NFAs in the powerful settings will be a little bit more complicated. But before we proceed with anything further along the non-deterministic finite automaton, what we're going to do, I would like to do, is to show you a couple of examples of NFAs and the languages they recognize, the kinds of strings they accept, and also for us to get a little bit more experience with processing NFAs, and then we will proceed to formally defining non-deterministic finite automata and proving that NFAs and DFAs are equivalent.